In this lesson, we will discuss the various nozzle and gating styles available in hot runner systems today, including the open or sprue gate, hot tip gate, and valve gate methods. We will also examine the methods used to control the temperature in the nozzle and gate area. The hot runner nozzle, also called the hot drop, is the connection between the manifold and the mold cavity. The position of the nozzle and how it seals to the manifold is critical to the hot runner molding process. If a nozzle is not positioned correctly, it can result in nozzle and gate damage, along with material leakage. Nozzle sealing is accomplished by spring force, thermal expansion, or by directly bolting the nozzle to the manifold. Virtually all nozzles have some alignment feature, usually a high tolerance surface in the gate detail that is used to ensure that the nozzle tip is aligned properly with the gate. During heating and cooling, the top of the rigidly attached nozzle moves as the manifold contracts and expands. There must be a robust seal between the nozzle housing and the manifold. Most hot runner nozzles utilize thermal expansion to provide the primary seal between the nozzle tip and the gate insert. Failure to run a hot runner at the recommended mold and nozzle temperature could lead to seal failure, resulting in damage or plastic leakage. The amount of thermal expansion is critical as it generates the force that prevents leakage between the nozzle tip and gate. Too much force may damage or deform the metal here. Too little and plastic leakage may result. The nozzle must be heated to maintain the melt temperature. There are two primary techniques for heating the nozzle: indirect heat and direct heat. If the nozzles or drops are heated indirectly, they do not have a specific nozzle heater, but rather rely on conductive heat from the manifolds as their primary heat source. Heat is conducted from the manifold metal to the nozzle housing to the nozzle tip. The nozzle material has to be highly conductive to transfer this heat efficiently. Some manufacturers use heat pipes to improve the conductivity to the nozzle. These highly conductive inserts work to evenly distribute the heat provided by heaters in the manifold. With indirect heat, however, some heat loss along the length of the nozzle is unavoidable. This results in a lower temperature at the nozzle tip as compared to the base of the nozzle. In addition, the nozzles have to be insulated, especially in the tip region, to minimize heat loss to the cavity. Indirectly heated nozzles are recommended only when molding plastics with a wide processing temperature window, as precise temperature control is difficult. Directly heated nozzles have individual heaters. This method of heating is extremely effective because within each drop, the temperature can be controlled right up to the nozzle tip to provide a higher degree of process adjustability and repeatability. There are several ways this heating element can be connected to the nozzle body. The element can be bonded, encapsulated, sintered, or hot pressed into a milled groove in the nozzle body. Some types of nozzles will have heater bands secured directly to the outside of the nozzle body. This contributes to good temperature uniformity. Whatever the design, temperature uniformity in the nozzle is critical, particularly when molding engineering plastics with a narrow process window. Direct heating uses more heating circuits to provide separate temperature control of each nozzle, allowing the molder to fine-tune and optimize the process. However, the additional wiring required for direct heated nozzles is more complex, presents more potential failure points, and can be more expensive than the indirectly heated nozzle type. The gate area is where the plastic part and the nozzle tip meet. The term gate is also used to refer to the specific type of nozzle design. There are two basic types of Hotrunner gates available: the open gate, also called a thermal gate, and the valve gate system. Within these groupings, there are literally hundreds of gating options available, depending on the part design, material type, desired gate vestige, and other factors. The design and temperature control of the nozzle tip and gate area is critical in Hotrunner molding. Let's examine the characteristics of each gate type. The open gate design, sometimes referred to as a thermal gate, uses precise temperature control of the nozzle tip to melt the plastic in the gate each cycle. The gate remains open for plastic flow during the filling and packing phase of the injection cycle. Then, during the holding phase, the plastic within the gate cools sufficiently so that it freezes, acting as a plug. This plug prevents the viscous plastic contained within the nozzle from oozing out into the cavity during the mold open and ejection phases. The gate is also the break-off point. At the time of part ejection, some of the gate material remains with a finished part and creates a vestige. The size and shape of this vestige is dependent upon the size and shape of the gate, temperature control in the gate, and the molding conditions. When injection pressure is applied to the melt at the start of the following cycle, the rise in pressure forces the plug into the cavity, remelting it as the cavity starts to fill. Due to shear heat generation, the actual temperature of the nozzle tip will increase as the melt flows through it. This particular gate type is often referred to as a hot tip or pinpoint gate. The melt and nozzle tip temperature in an open gate system can sometimes be a difficult temperature control problem. The temperature of the mold steel and the hot tip can be several hundred degrees apart. It is often necessary to insulate this area to prevent heat transfer. Titanium alloys are also used as a thermal insulator where low thermal conductivity is required. Designs that provide temperature insulation through air gaps or solidified plastic can be an alternative. Conductive materials such as beryllium copper are used to conduct heat from the nozzle heater to the tip and maintain the desired temperature at the gate. Selection is critical in the design of nozzle tip components. Materials with low thermal conductivity are used where contact is necessary with the mold, but minimal heat transfer is desired. Materials with high thermal conductivity, such as copper alloys, are used to conduct heat from the nozzle into the gate area. Copper alloys, however, do not have good wear properties and tend to be worn away over time. Tungsten carbide alloys are used where good thermal conductivity is required in conjunction with excellent wear properties. This is a hot tip or pinpoint nozzle tip. It provides acceptable gate appearance for many applications. The hot tip is commonly used for caps and closure applications, but can also be used for larger parts. This type of nozzle tip will typically leave a small gate vestige on the molded part. Smaller gate sizes will give reduced gate vestige, but will also subject the material to more shear and require increased injection pressures. The hot tip relies on good nozzle tip temperature control as well as adequate gate cooling to optimize gate appearance. The thermal sprue type gate, sometimes called a hot sprue, relies on cooling in the mold to freeze the gate. This will result in a larger gate vestige that looks like a small sprue. The thermal sprue gate is commonly used to feed into subrunners or other components where gate appearance from the hot runner is not as critical. It subjects the material to a minimum amount of shear heat generation and pressure drop. This type of gating is not recommended for materials that have a tendency to string, like polyethylene, polypropylene, and polystyrene. The multi-point tip provides several hot tip gates from a single nozzle. These can be used to gate several parts, usually smaller parts, with one nozzle or to provide several gates onto one part. It is commonly used to mold components such as gears, where concentricity is critical. This gate type has only one zone of temperature control for several gates, which can limit processing options. The edge gate or side gate method provides an open thermal gate into the sidewall of the part. The gate is sheared from the part as the mold opens. The part design must be suitable to provide a clean shearing action. Good temperature control in the gate area is also required. A cold slug forms in the gate, preventing gate drool. On the next cycle, injection pressure forces the plug into the cavity, remelting it as the cavity starts to fill. The control of gate solidification is influenced by the properties of the plastic. For example, different gating techniques are required to process semicrystalline and amorphous plastics. Semicrystalline materials have a higher melt temperature, so generally, the nozzle must supply more heat to the gate area than for amorphous plastics. Because semicrystallines melt and solidify with a narrow temperature range, it is important that the nozzle tip temperature be kept as constant as possible. If allowed to cycle above and below the melting point of the material, plastic may solidify in the gate. This is extremely critical when molding with a filled type semicrystalline material. Common semicrystalline materials include polyethylene, polypropylene, nylon, acetal, and PET. When molding an amorphous material, the gate area should be thermally insulated from the nozzle and nozzle tip. Otherwise, heat transfer from the nozzle to the gate area will delay solidification of the amorphous material, leading to defects like gate stringing or increased gate vestige. Common amorphous plastics include polycarbonate, polystyrene, and ABS. Valve-gated hot runner systems offer the molder the optimum in flow control. The valve gate is often used for fill sequencing, processing foamed materials, gas assist molding, or where minimal gate vestige height is required. A valve gate uses a pneumatically or hydraulically operated valve stem to mechanically open or close the gate. The gate opens at the beginning of the injection stage and allows the viscous plastic to enter the cavity. When injection and packing are complete, the valve stem piston is actuated forward. This shuts off the resin flow and the tip of the valve stem effectively forms part of the cavity surface. The result is a circular gate vestige, the same size as the gate diameter, that looks similar to an ejector pin witness mark. The valve stem tip never actually makes steel-to-steel contact. There is always a thin film of plastic left between the pin and the gate. The valve gate method also prevents drool and stringing in the gate. In addition, the physical properties of the molded part are improved with the use of a valve gate. Due to the larger gate opening, valve gates provide easier part filling and generate less shear than thermal gates. Also, the holding pressure can be applied and controlled for a longer period of time, resulting in more uniform packing. The result is a part with less warpage and improved physical properties. There are two basic types of valve gate seals, tapered and cylindrical. Each type has a different method of sealing the gate. Let's first examine the tapered shutoff system. Here, the tip of the valve stem is ground at an angle that seals to a matched angled surface in the gate insert. As the valve stem moves forward, the melt caught between the valve stem and gate steel is compressed and forced to flow out of the gate. A seal is formed between the valve stem tip and the gate insert. The forward stroke of the valve stem must be limited with a physical stop to prevent damage to the gate insert from the valve stem hitting it. With a cylindrical valve stem seal, the valve stem creates gate shutoff without metal-to-metal contact with the use of a tight tolerance slip fit in a cylindrical gate. When the stem moves forward, it acts as a plunger, forcing the melt from the gate opening into the cavity. This gating style relies on the tight tolerance between the valve stem and gate opening for the superior gate quality. This feature also minimizes any gate wear and allows up to 10 million shots without any gate repair. Besides minimized wear, the cylindrical type shutoff allows for unsurpassed optical gate appearance. The cylindrical sealing, however, is more sensitive to wear if the required tolerances are not maintained, causing rapid degradation in gate quality as the wear increases the size of the gap between the valve stem and the gate steel. Therefore, cylindrical seal valve gates require precise alignment of the valve stem to the gate in order to reduce wear. Ideally, positive guidance of the valve stem in the nozzle tip prevents collisions between the valve stem and gate steel. Valve gate nozzles can also reduce cycle time, especially when molding large parts. Since the valve, and not the molding machine, holds pressure on the cavity, you don't have to wait for the gates to freeze, and melt plastication can begin sooner. With the open or thermally gated nozzles, the gates must be sufficiently frozen before hold pressure can be released and screw recovery can begin. This difference can add several seconds to the cycle time for thermally gated parts with large gates. Also, the valve gate's lower shear rate in the gate area minimizes shear heating of the melt, reducing the part's cooling requirements. Sequential valve gating is the independent control of valve gates in a mold. The precise timing of the opening and closing of the valves can eliminate weaknesses or weld lines or control their location on the molded part. Sequential valve gating is also used to control the filling of parts with dissimilar mass, like family molds. Each valve gate is independently opened and closed at a predetermined event. For example, time, screw position, or cavity pressure. This will provide complete control of cavity filling. Valve gate nozzles can be especially useful for thin wall molding. Rapid fill rates, high pressures, and fast cooling characterize thin wall molding applications. Rapid fill rates, in the range of a half second or less, are often necessary to fill the cavity before the frozen layer thickens and prevents further cavity filling. The large gate diameters with reduced flow restrictions allow fast filling while minimizing pressure drop and shear heating. In many thin wall molding applications, rapid part cooling permits the valve stem to close immediately after the cavity is filled. A thermal gate would require additional cooling time for the gates to freeze. Valve gates have been successfully used with abrasive plastics containing fillers such as glass and carbon fiber. However, care must be taken that wear-resistant materials are used for the valve stem and nozzle tip. Tapered valve gates are more often recommended for abrasive applications. Different types of open or thermal gates have different types of processing characteristics. Open gates with large orifices are best suited for filling large parts and molding with abrasive materials because the pressure drop and shear stresses are low. Open styles with smaller orifices have higher pressure losses and shear rates and are more susceptible to wear. The valve gate method is best for eliminating drool and gate stringing and minimizing the height of the gate vestige. In addition to the superior gate quality, valve gate nozzles can improve the part's physical appearance and increase productivity. However, valve gates have moving parts and will usually require a higher degree of preventive maintenance than open gate systems. Specialized training may also be required to properly operate and maintain a valve gate Hotrunner system. Valve gate systems are also more expensive than the cost of a thermal gate design. In this lesson, we examine the various nozzle and gating styles available in Hotrunner systems today. In the next lesson, we will describe how the temperature is controlled in the nozzle and manifold of a hot runner, as well as discuss some common hot runner applications.